In today's lesson, we are going to be looking at creating and using quadratic expressions. So this is going to be a little bit of review from grade 10. We'll see later, hopefully, the connections, or hopefully you remember some of these concepts. So just as a little bit of a warm-up, without counting every tile, how can you determine how many squares are on the outside of this border, or outside of the border of this 8 or 10 by 8 figure? So basically all these squares in orange. We know it's a 10 by 8 figure. So how could you count, or how could you determine how many squares are in that outside border without literally going through and saying, okay, 1, 2, 3, 4, 5, and so on? So again, a little bit of a warm up to figure that out. Right? Maybe, and I'll give you a hint, there are different ways you could do this, but maybe perhaps look at maybe the shape of the overall and then think about what we're taking or getting rid of, which is everything in here, right? And thinking about what kind of shape that would be. Another warm-up is the same idea, moving on to an 8 by 6. So we'll go through this one together, right, without counting every tile. So one way that you could do this is say, okay, well, the whole shape is 8 by 6. So there's 8 by 6, that's how many tiles there are as a whole. Now, the inside, just by looking at it, it's one, or it's 2 tiles less, right, one on either side. So if I'm looking at everything on the inside, in white, that's going to be 2 units less, or 2 tiles less for the length. So it's going to be a 6 by 4 tile instead. And what I can do, if I just want the border, I can take the whole shape minus the inside shape, and that will give me the border. So 8 times 6 is, so I can try to do the math in my head, 8 times 6, I believe, is 48. I'll double check that because my multiplication tables in my head aren't going so well. Yep, it is 48. Minus 24 is 24. So there are 24 tiles on the border. There's other ways you could do it. That is one way that you could. Now, what if it was an n by n minus 2 figure? So same idea. We have our border. We have one that is n and the other one that is n minus 2. And we want to find the outside border. So we kind of look hypothetically at something like that. What would the inside be represented as? How could we represent the inside? Well, if we look at the past example, right, we had an 8 by 6 and we subtracted a 6 by 4. This was the whole shape. This was the inside shape. So if I look at this one, or if I look at how the values compare, I at least know from my whole shape, I know it's going to be 8, or not 8, sorry, it's going to be n times n minus 2. And then what would the inside be? What would the inside that I have to subtract be? Well, if we look at the comparison, the inside was 2 less in both dimensions. Outside was 8 by 6, inside was 6 by 4. So 2 less on each one. So if I look at my whole, well, what's 2 less from n? That's n minus 2. And what's 2 less from n minus 2? Well, n minus 4, because n minus 4 is 2 less. Right? We've subtracted 2 again. So this would be my expression. And this would tell me how many tiles would be on the inside of any given side length, so long as the other side length is 2 less. Now, obviously in our answer, we went through and we found out that it was 24. In the example here, though, how would we simplify this? We don't have any numbers to multiply. And we have multiple terms to multiply. What we're going to do, and hopefully this rings a bell, is we're going to FOIL or distribute right? Or expand or multiply our brackets. So n times n becomes n squared minus 2n. And on the other side, we're subtracting. We have n squared, n times n, minus 4n minus 2n plus 8. Now we're going to go through and simplify before we subtract everything. N squared minus 6n plus 8. And because I'm subtracting everything, all the signs in this second bracket are going to change. So minus n squared plus 6n minus 8. I can go through and collect some like terms, like my n squareds here, my n's. So I end up with n squared minus n, which is just 0. That cancels out. Negative 2n plus 6n is 4n, and then minus 8. So that is a quick way, or this is a formula or expression now that we can use to help us determine the number of tiles for the border. Now, if this part was complicated, don't worry. The main thing we're going to focus on, though, is what we've done up here, right? The multiplying of our brackets, the multiplying of something into a bracket with multiple terms. So that's what we're going to focus on. So we'll look at another example, right? So for example, I want to use antique frames as artwork. So I found one at the antique market on the weekend. The dimensions of the widest part of the frame are 68 by 78. The frame itself is X centimeters wider than the area for the picture. I want to develop an expression for the area of the picture that would fit in this frame. So it's kind of the opposite in what we were looking at. I want to find an expression for this area, everything that would fit in here. So it is a rectangle, so I need to do the area is equal to length times width. So I need to somehow represent the length and the width for this inside figure. I know the overall dimensions, 68 by 78, and I know that whatever the width of the frame is considered X. So how could I use that to help me come up with my dimensions? Well, if the overall thing is 78, we'll say the height, or the length, the overall length is 78, and I'm taking away an X on the top and an X on the bottom, the length for this picture frame, or the picture itself, not the frame, would be 78 minus 2x. The width, which is this portion here, if the entire frame is 68 and each portion it's equally distant around is x, then I would subtract an x on either end. So the width would be 68 minus 2x. So now I have two expressions for the length and the width of this picture frame. Or not the frame, sorry, the inside of the picture frame. So if I want to find the area, which is length times width, I have my two new dimensions, 68 minus 2x times 78 minus 2x. And now I just need to multiply. So how do I multiply these two brackets? Again, going to what we looked at in grade 10, we're going to use what's called the distributive property. And essentially, that is everything in the first bracket has to multiply everything in the second bracket. So I'm going to use arrows to help show that. So the 68 is going to multiply the 78 and the negative 2x. The negative 2x is going to multiply the 78 and the negative 2x. So I'm going to go through. I'm going to write this out fully. Actually, let me just move this down to give myself more room. I'm going to write this out fully. Now, you may skip this step if you are comfortable with multiplying. You can go right to the answers. So this step right here that I'll put in purple is going to be different, or kind of an in-between step. So 68 times 78, plus 68 times negative 2x, plus negative 2x times 78 plus negative 2x times negative 2x. Let me just move this over. I'll put it down here so it fits. So this was an in-between step, right? You might not do this in-between step if you know what you're multiplying, and you might just go to this next part. 68 times 78 is 5,304. 68 times negative 2x is negative 136x. Negative 2x times 78 is negative 156x. And negative 2x times negative 2x is plus 4x squared. So you might just go from here to here without doing that everything in purple, which is fine. If you need to do the step in purple, by all means, go ahead. To kind of show your work, to kind of make sure you don't get lost. Then the last step is going to be collecting any like terms. I do have some like terms with the x's here. I have two terms with x. And in terms of writing it out, generally speaking, we want to write it out so that the variable or the letter with the highest exponent is at the front. So we have 4x squared at the front. We're going to combine our two like terms with the x's and get negative 292x, and then plus 5,304 at the end. So this final thing, that is an expression for the area of the inside of the shape. Now the x is going to be dependent on what the width is of that shape, but that is the general expression. So this was more of an application of what we're going to be looking at. And what we're going to be looking at is expanding and simplifying our distributive property. So when you multiply two expressions, each term in the first expression must be multiplied by each term in the second. You might have heard of the FOIL method, specifically when we're multiplying two terms by two terms, right? So you might have heard the FOIL or the rainbow method. That's kind of basically what we're doing when we have the arrows kind of showing what's being multiplied. It kind of looks like a rainbow, or foiling first, outside, inside, last. Different things that you could use. Again, think of it as kind of a combo meal, right? One combo meal has all four items, right? A pop, a burger, fries, and a cone. If I get multiple of those, right? Say I get 4 combo meals, that's 4 of each item, not just 4 of one item and then 1 of the rest. So this 4 of each combo meal works out to, again, just kind of quickly draw it, 4 of the Cokes plus 4 of the burgers plus 4 of the fries plus 4 of the cones, right? So the idea is that this 4 applies to everything in that combo or in that bracket. Same idea with distributive property. The number that gets multiplied applies to everything in that bracket, not just the first one. So let's just go through some examples and look at multiplying or expanding the following expressions. So I have x times 5x minus 6. Kind of a straightforward example, very simple, things that you might have even seen in grade 9. So this x has to multiply to both terms inside that bracket. So x times 5x, I multiply the x's together, I get 5x squared. You kind of multiply like terms. So x times the x, the 5 is still there, right? Because this would just be a fancy way of saying is 5 times x, and then multiplied by another x. X times x is x squared, and the 5 is still there. X times negative 6 is negative 6x. I then want to look to see if I can collect any like terms, right? I do have x's in both. However, one is an x squared and one is an x, so I can't add them or subtract them in this case. They have to stay separate. B, similar idea, just more terms inside the bracket, so that means I have to multiply the 4x to more things. So the 4x times the 3x squared, 4 times 3 gives me 12, x times x squared gives me x to the power of 3. And then multiply 4 to the next one. 4x times negative 2x is negative 8. And then the x's multiply to x squared. And then lastly, 4x times 5, I get positive 20x. So you're looking at multiplying, again, like I said, like termed, either numbers or the variables. If there's nothing that's the same, then we kind of just carry it through. C, a little bit more challenging, right? We have a number times a bracket times another bracket. Now, when we're multiplying, order doesn't matter. So there's different ways that you can go about multiplying this. I would probably suggest the easiest thing to do first, though, is multiply the number into the bracket. So this gives me negative 6z plus 3. So negative 3 times 2z is negative 6z. Negative 3 times negative 1 is positive 3. That answer is now being multiplied to the next bracket. So negative 6, and then here, so I'll bring it down a bit. So just again, kind of going back a bit, that negative 3 does not multiply into the 4z plus 1, right? If we think of it as kind of a set of 3 numbers, right? So 3 times 2 times 1, or we'll do 3 times 2 times 4. I don't do 3 times 2 and 3 times 4, right? I do 3 times 2 to get an answer, which is 6, and then I multiply that answer by 4 and get 24. Similar idea here. We multiply these two together to get negative 6z plus 3, and then I take that and multiply it by the next bracket. Right, so just some kind of things to think about. I only mention it because I've seen that kind of mistake come up before. Now I have one bracket times another bracket. I'm going to use distributive property or my foiling, right? So the negative 6z multiplies both terms, and the 3 also multiplies both terms. Again, I'll show this middle step in purple that you don't really have to do if you're comfortable with multiplying. But if you aren't, again, feel free to use this. So negative 6z times 4z plus negative 6z times 1 plus 3 times 4z plus 3 times 1. So again, that step is kind of an in-between. You might not show that. Now I'm going to multiply each pair. So negative 6z times 4z is negative 24z squared minus 6z plus 12z plus 3. I'm going to find that I do have a pair of like terms here that I can add. Or, yep, in this case add. So I'm going to have negative 24z squared. Negative 6z plus 12z is positive 6z plus 3. So again, I collected my like terms. I put the term that had the highest exponent first, or on the letter, and then in descending order. So squared, no exponent, or 1, and then no letter at all. D, similar to what the last one, except it's written a little differently. And the key difference here is this little squared. So the squared actually means multiplied by itself. So I could actually rewrite this, and I am going to have to rewrite this to make it a little bit easier. 2 times 5x plus 3 times 5x plus 3. So because it's squared, it's multiplied by itself, right? And it's the same kind of setup as the last one. I'm going to multiply the 2 into the first bracket. I get 10x plus 6. Then that answer is going to multiply the 5x plus 3. So you might say, well, why don't I do the exponent first? And you could. So you could do 5x plus 3 times 5x plus 3 and then multiply your final answer by 2. That's fine as well. Or because if we're breaking it down and rewriting this to show that it's just 3 numbers multiplying, then order doesn't really matter. There's no bedmass when it's all the same operation. I have 2 brackets multiplying each other. I'm going to use the distributive property, the FOIL method, or the rainbow method. Again, I'll show this in-between step. So we have 10x times 5x plus 10x times 3 plus 6 times 5x plus 6 times 3. That then simplifies to 50x squared plus 30x plus 30x plus 18. I do have like terms, the two terms with x. So I'm going to rewrite this as 50x squared plus 60x plus 18. And that's my expanded and simplified expression. Two more examples, again, just getting a little bit more complicated, involving some collecting like terms now. But again, similar idea to what we've done before. I'm going to distribute here. And on the other side of subtraction, I can also distribute. Use the FOIL method. So I get 6a squared plus 8a minus, and because I'm subtracting whatever this answer is or whatever the product is of these two terms being, or these two brackets being multiplied, I'm going to put a large bracket here to show that I have to subtract everything. So I'm going to kind of do this in a shortcut, or just removing that middle step. So 5a times 4a is 20a squared. 5a times negative 3 is negative 15a. 1 times 4a is plus 4a, and 1 times negative 3 is negative 3. I can simplify some terms inside these brackets. So I'm going to go down to my next line. I'm still subtracting everything in that final bracket. I have 20a squared. I can combine the two a terms and get negative 11a minus 3. Now I can apply this negative. We could think of it as an imaginary 1, or an invisible 1. So we would have to multiply this negative 1 through to everything. But negative 1 doesn't really change the number, it only changes the sign. So this actually becomes 6a squared plus 8a. Again, nothing has affected that yet. Multiplying everything in the bracket by negative 1 makes it negative 20a squared plus 11a plus 3. So again, same thing, just the sign has changed. I'm going to look for some like terms. I do have some like terms with my 6a and negative 20a, and I do have other like terms with my 8a and 11a. I can rewrite those, or rewrite this, combining those like terms, putting the squared term first. So I have negative 14a squared plus 19a plus 3. So again, same kind of steps, just a little bit more complicated, some more steps involved, but still the same idea of distributing the property and simplifying. For f, again, same idea. I'm going to distribute the 7n through the first bracket, and for the second bracket, I'm going to multiply the whole thing of negative 3n squared into the second bracket. By multiplying the negative through, it saves me from having to multiply it through later. So this becomes 21n cubed plus 14n squared minus 6n cubed plus 12n squared. Now I can go through and look for like terms. I do have two terms with n cubed and two terms with n squared. So I can combine those two and I get 15n cubed plus 26n squared. And again, I'm putting the n cubed first because it has a higher exponent, followed by the n squared. So again, same idea, distributive property, expanding, collecting like terms. Right? Hopefully this is reviewed. Distributive property was taught in grade 9. This binomial expansion, the foiling, two numbers in a bracket times two other numbers in a bracket, or two terms in a bracket times two other terms. Right? That's something you did in grade 10. So this should be familiar to you. Right? If not, please make sure you are practicing, because a lot of what we look at in this unit is going to require an understanding of how we multiply terms like this.